Welcome back. Now we're going to talk about vector addition. So suppose we have some vector, notice that's bold, so if you were writing this on your paper, you might draw a little vector notation above it, but we have u equal to some vector, which we'll call AB on this triangle. And then we have v, vector v, goes from B to C. So we have little vector u and little vector v. The sum of vector u plus vector v, or rather the sum of AB plus BC, that equals this diagonal form. So notice when I'm drawing this and I'm adding this vector, I drew my vector, and then at the tip of B, I drew vector BC. I drew my vector V, right? So it's continuing off of B, there's C affecting it, and it creates this AC here. AC is what we call the resultant. So this doesn't literally mean I can just add these two vector values together and get the resultant. We have to do some trig in order to figure it out. But the initial point from A, so we started at A and we ended at C. That's my terminal point. So from the initial point to the terminal point, adding those vectors by putting the second vector at the tip or the terminal point of my first vector, that creates my resultant. And since addition is commutative, vector addition can also be described using what we call parallelogram law. So if you think about this here, we have the red vector plus the blue vector. This triangle right there matches this triangle here. So vector u plus right there, vector v. That gives me my resultant. And I could also say v plus this vector up here, u, v plus u, will also give me this resultant in the middle. Okay? So for that reason, we generally, when we're working these problems, we're just going to draw u and v. We'll have them both starting at the same spot, and they're acting together to create this resultant in the middle. We use our parallelogram law. So u plus v is equal to v plus u. Both of those end up at that same point up here in the top right corner where my resultant stops. All right, u plus v is equal to v plus u. One thing to keep in mind when we start drawing these pictures and we're representing them with vectors, especially when we think about a force acting on an object, our tendency is to say, well, the force is pushing that object. But if you think of it as a pull going outwards, or the wind is pushing the boat, but thinking about the wind pulling the boat forwards, it might make your picture easier to draw. For this reason, we use this logic then to consider two forces acting on an object and the combined effect of those two forces. So as I said, if we have an object right here at this point, there's my object, that big dark dot at the vertex. Now I could think about it as two vectors acting on that point. And then the resultant would again be that diagonal of the parallelogram that we would eventually form. And we could do this infinitely. But it's easier for us to think about that as a pull. So if we think we have force 1 is going to move the object in this direction, force 2 would move the object in this direction, then my resultant here in the middle would be force 1 plus force 2. Now, again, I just want to remind you, this doesn't mean we can add two forces. It doesn't mean if this was 10 pounds or newtons and this was 5 pounds or newtons, we couldn't just say, well, this is 15. That's not the way it works. We've got to use some trigonometry. But the idea is that these two would come together and create this resultant, which represents the sum. So here we have a problem. We have forces of 15 newtons and 25 newtons acting on an object at right angles to each other. We want to find the resultant vector as well as the angle it makes with the larger force. So as I just said, and per that rule up above, this does not mean I can take 15 plus 25 and add them to get 40. The length of this is not going to be 40. All right, so we're looking for that magnitude of the combined forces. So let's draw a picture. Let's say we have a 15 Newton force. So there's my 15 and my 25 Newton force, and they're acting on this object at right angles. It's not drawn perfectly to scale, but you will notice I drew my 25 Newton force longer than my 15 Newton force. So if I think about creating a parallelogram, and since these guys are right angles, that parallelogram is going to be a nice rectangle. And we know where the resultant will fall. The resultant is going to start at that initial point of both of the vectors and end at the opposite point of that diagonal. So that's my resultant. I'm looking for the magnitude of that vector. What we want to do then is extrapolate a triangle. We have two right triangles here. I have this triangle on the top or this triangle, on the below right side. Now this says find the angle that it makes with the larger force. So the resultant makes an angle with the larger force, 25, and also down here, the smaller force, 15. We're going to pick this angle. So I'm going to extrapolate or pull out that right triangle and try to keep it to scale. So what we have here is we have a side, vertical side that is 25. We're interested in this resultant's length. Also, we're interested in this angle, theta. Now, what is the length of this side up here? So this top side is going to be 15. So we're trying to find the angle theta and also the length of this hypotenuse, r. We can do two things. Since this is right triangle trig, and keeping in mind that's a right angle up there, this is a rectangle, this parallelogram that we formed, right triangle trig. So what is r? Well, Pythagorean theorem, 15 squared plus 25 squared is going to equal r squared, or rather, r is the square root of 850. Now, it could be plus or minus, but we know since these were both positive forces that this is going to be a positive force. All right? Also, we want to find theta. Well, I can use root 850 because that's an exact number, but I can also use 15 and 25. And how do 15 and 25 relate to theta? They're not the hypotenuse. We have the opposite and adjacent side. And opposite and adjacent means we would use tangent. So tangent of theta is 15 over 25, or rather, tangent theta is 3/5. Isolating theta, we would use inverse tangent of 3/5. And if you type that in your calculator in degree mode, you're going to get approximately 30.96 degrees. Now we want, since we're dealing with something in real life that we're looking at on this paper, we want a degree answer, not a radian answer. And if you're in radian mode, you will get the incorrect answer here. So the magnitude of the resultant, the magnitude of r, is the square root of 850, and I don't feel I need to plug that in my calculator and round it. And then theta is approximately 30.96 degrees. So in this video, we talked about the sum of two vectors and how to find that resultant using a parallelogram law. In this specific example, we had a nice right triangle, which allowed us to use the Pythagorean theorem and SOHCAHTOA, but moving forward, most of our examples are going to be oblique triangles where they do not have a 90-degree angle in them.